Good morning, students. Just after the completion of the chapter Chemical Kinetics, Electrochemistry, Solution, next we go to another one very important chapter that is known as Coordination Compounds. Coordination Compounds. What is the coordination compound? Today, in this chapter, I will try to complete the introduction part. What is a normal salt, double salt, complex salt, the difference between double salt and complex salt, then ligands, types of ligands, what is oxidation number, what is coordination number, how to calculate the oxidation number and coordination number for a central metal ion, what is the ionizable part, what is the non-ionizable part, what is the coordination sphere, and finally the IUPAC. By using the IUPAC system, how the name of inorganic compound or complex compound given. So before going to, let us start one by one. First one is the introduction part. The coordination chemistry. The coordination chemistry is a branch of inorganic chemistry which deals with the study of coordination compound or complex compound. I repeat again. Coordination chemistry is a branch of inorganic chemistry which deals with the study of coordination compound or complex compound. What do you mean by coordination compound? It is a type of compound in which the central metal atom is surrounded by cluster of ions or molecules through a coordinate bond or a dative bond. Again, that complex compound may be cationic complex, anionic complex, or a neutral complex. So before going to in detail about the complex compound or coordination compound, it is necessary to cover some terminology. Let us discuss one by one. First one is normal salt or simple salt. What do you mean by normal salt? First one is normal salt. What do you mean by a normal salt? That means a salt is defined as a compound. Salt is defined as a compound which is formed by replacing replaceable hydrogen atom of an acid by metal atom. I repeat again. A salt is formed. A salt is a compound which is formed by replacing replaceable hydrogen atom of an acid by metal atom. For example, HCl, hydrochloric acid, gives only one type of salt, that is sodium chloride or potassium chloride. B2, sulfuric acid provide two type of salt, that is NaHSO4 and Na2SO4. B3, phosphoric acid S3PO4 provide three types of salt, that is NaH2PO4, Na2HPO4, and last is Na3PO4. Mark that. From this example, it is clear that the number of hydrogen atom present in the acid are replaceable, but it is not always true. It is never keep in your mind that the total number of H present in an acid are replaceable. For example, mark that. Acetic acid CH3COOH. Acetic acid, from this formula it is clear that it has 4 hydrogen atoms, but among them only one is replaceable. That is, it provides only one salt, that is sodium acetate. These are some common examples of normal salt or simple salt. Again, normal salt or simple salt classified into acidic salt, basic salt, neutral salt. If the salt solution pH is greater than 7, then it is known as basic salt. If the pH of the resulting solution is less than 7, then it is known as acidic salt. On the other hand, if the pH of the solution is 7, then it is known as neutral salt. Next we discuss about what is a double salt. Next is double salt. Second one, double salt. What do you mean by double salt? It is a form by taking equimolar proportion of two simple salt. I repeat again. By taking equimolar proportion of two simple salt when added to water or added to aqueous solution and concentrated, then cooled, then the compound form is known as a double salt. Double salt is formed by taking equimolar proportion of two simple salt. For example, between potassium, formula potassium sulfate, aluminium sulfate, 24 water, more salt, formula ferrous sulfate, ammonium sulfate, 6 water. Another example, carnallite, potassium chloride, magnesium chloride, 6 water. Mark in this example, it is a simple salt, it is a simple salt. Equimolar proportion 1:1. It is a simple salt, it is a simple salt. Equimolar proportion. It is a simple salt, it is a simple salt. Equimolar proportion. So when two simple salt in equimolar proportion added to aqueous solution, concentrated and finally cooled to get the crystal known as the double salt. The most important thing is that this double salt only exists in solid form. It loses its identity in aqueous solution. I repeat again. The double salt only exists in solid form. In aqueous solution, it loses its identity. And it gives the taste of the constituent ion from which it is prepared. For example, potassium gives the taste of potassium, aluminum and sulfate ion. And here, in double salt, the same metal atom possesses its normal valence. Then we discuss another one term, that is complex salt or coordination compound. Next we discuss third, coordination compound or complex compound. What do you mean by complex compound or coordination compound or complex salt? It is slightly similar to double salt. In double salt, we select two simple salt. Here also two simple salt. In double salt, equimolar proportion of two simple salt. But here, molar proportion of two simple salt. When added to aqueous solution, concentrated and cooled, the crystal form is known as coordination compound or complex compound. The difference is that in double salt, that is equimolar proportion, here is molar proportion. And here the complex compound exists in solid form as well as in aqueous solution. It gives the taste. It does not give the taste of the constituent ion from which it is prepared. The complex compound, the form, not give the taste of the constituent ion from which it is prepared. Suitable example, when excess of ammonium hydroxide added to copper sulfate solution. Mark that. I repeat again. When excess of ammonium hydroxide added to copper sulfate solution, a deep blue color complex is formed. Deep blue color solution is formed. That is due to the formation of a complex compound. I repeat again. Mark that. CuSO4.5H2O plus 4 molecule of ammonium hydroxide give rise to tetraamine copper 2 sulfate plus 9 water. It is a complex, deep blue colored complex. Its name is tetraamine copper 2 sulfate. Mark that. I repeat again. When excess of ammonium hydroxide added to a copper sulfate solution, a deep blue color complex is formed. This is known as complex compound. Here, this copper is known as central metal atom, which is attached to either a neutral molecule or ions by a dirty bond or coordinate covalent bond. These molecules are known as ligands. The most important thing is that this complex, the tetraamine copper 2 sulfate, this complex form does not give the taste of copper or does not give the taste of ammonia. Its behavior character is completely different from those of the constituent from which it is prepared. And it exists in solid form as well as in aqueous solution. And the most important thing that the central metal atom in the complex salt possesses two types of valency. One is known as a normal valency or a primary valency. One is known as a secondary valency. One is known as a primary valency. One is known as a secondary valency. Then we discuss what is the difference between double salt and complex salt. Very, very important 2-mark question. Give a comparison, give a comparative idea about the double salt and the complex salt. Difference between double salt and complex compound, complex salt. One side double salt, one side complex salt. While writing the difference between two species, it is important. Always point one is definition. So point one is definition. Here definition. What is the definition? In case of double salt, two simple salt in equimolar proportion get concentrated and cooled, get the crystal that is known as a double salt. But here, two simple salt in molar proportion get concentrated, cooled, and the crystal form known as complex salt. Point 2. It exists in solid form only. It exists in solid form only. It exists in solid form as well as in aqueous form. Point 3. It loses its identity. It loses its identity in aqueous solution. But it retain or maintain its identity in aqueous solution. Next point. It gives the test. It gives the test of the constituent one. Give the test of the constituent from which it is prepared. From which it is prepared. It gives the test of the constituent from which it is prepared. It does not give the test of the constituents from which it is prepared. Next, in double salt, it contains the ionic bond. But in complex salt, in complex part, there is no presence of ionic bond, rather there is the presence of coordinate covalent bond. Next, in double salt, the central metal atom in double salt, the metal atom exhibit is in normal valency. But here in complex part, the metal atom exhibit dual valency. One is known as a primary valency, one is known as a secondary valency. Primary valency gives an idea about oxidation number, while secondary valency gives an idea about coordination number. These are some points to distinguish between double salt and complex salt or coordination compound. Next, shift to another one term that is known as a ligand. Next we discuss, next term is ligands. What do you mean ligands? The atom or ion or molecules which are electron rich species and at least donate a pair of electron to central metal ion by the formation of a covalent bond forming a complex is known as a ligand. I repeat again. The ion or a molecule which are electron rich species at least donate a pair of electron to the central metal ion in the form of a dative bond forming a complex compound is known as a ligand. For example, mark that. One example is there, tetraamine copper 2 sulfate. It is one complex part. In complex part, after the inside the coordination sphere, this one is known as central metal atom. Central metal atom. Next, after the central metal atom, what is present? This is known as ligand. Then depending upon charge, depending upon the charge present on the ligand, ligands may be classified into three types. One is known as cationic ligand, one is known as anionic ligand, one is known as neutral ligand. Let us discuss one by one. Cationic ligand. If a positive charge is there, then it is known as a cationic ligand. For example, NO plus, NO2 plus, NH2, NH3 plus. These are some example of cationic ligand. Its name is nitrosonium ion. Its name is nitronium ion. Its name is hydrogenium ion. These are some examples of cationic ligand. Next is anionic ligand. If a negative charge is present, then it is known as anionic ligand. For example, Cl minus, Br minus, SO4 2 minus, CO3 2 minus, chloride ion, bromide ion, sulfate ion, carbonate ion. These are known as anionic ligand. If no charge is there, then they are known as neutral molecule are there, then it is known as neutral ligand. For example, NH3, H2O, PyNO, etc. Ammonia, water, pyridine, nitrosyl. These are some neutral molecule behave as a ligand, electron-rich species. So they are known as neutral ligand. Again, depending upon the number of a donor atom that donate a pair of electron in the formation of a dative bond, ligands are again classified into different types. I repeat again. Depending upon the number of a donor atom that donate a pair of electron in the form of a coordinate bond with the central metal atom, ligands are classified into monodentate, bidentate, polydentate, ambidentate, chelating, bridging. So many are there. Let us discuss one by one. Let us discuss the types of ligand. First one is types of ligands depending upon the number of donor atoms. One is monodentate or unidentate ligand. Next is bidentate ligand. Next is polydentate. Next is ambidentate ligand. Next is chelating ligand. Next is bridging ligand. Let us discuss one by one. First one is monodentate or ambidentate ligand. The ligand, it may be ionic species or a neutral molecule, electron-rich species, but contain only one donor atom. Then it is known as monodentate or unidentate ligand. I repeat again. The ion or a molecule, electron-rich species, which possess only one donor atom, only one donor site, which donate one pair of electron in the form of dative bond with the central metal atom, known as monodentate or unidentate ligand. For example, Cl minus, Br minus, SO4 2 minus, OH minus, etc. The most important thing is that it is to be noted that the monodentate ligand no doubt donate a pair of electron. That does not mean that it possesses only one pair. It may possess one pair, two pair and three pair of electrons. But only one donor atom donate one pair of electrons. Then it is known as monodentate ligand. Next, bidentate ligand. The molecule or the species which possess two donor site, two donor atom, which donate two pair of electron to one metal atom or central metal atom or ion, then it is known as bidentate ligand. Again, bidentate ligand is of two types. Bidentate ligand is of two types. One is known as symmetrical bidentate. Symmetrical bidentate. One is known as unsymmetrical bidentate. Not symmetrical bidentate. Means the bidentate ligand, two donor atom, if similar donor atom, which donate two pair of electron to central metal atom, then it is known as symmetrical bidentate. On the other hand, the bidentate ligand in which two donor atom are different one, then it is known as unsymmetrical bidental ligand. For example, one example, that is En, ethylene diamine, mark that, CH2, NH2, CH2, NH2, mark that. Here donor atom is nitrogen, here donor atom is nitrogen. Two are similar atom, so it is known as symmetrical bidental ligand. Another an example, OX, oxalate ion, that is CO minus, CO minus. Here donor atom is oxygen, here donor atom is oxygen, oxalate ion. So since both are donor atoms similar one, so it comes under symmetrical bidental. On the other hand, if the two donor atom is different one, then it is known as unsymmetrical bidental. For example, glycinate ion. Here example is GLY, that is glycinate ion. CH2, NH2, COO minus. Mark that here donor atom is nitrogen, here donor atom is oxygen. Both are two donor atom is there, donate two pair of electron, two dative bond is there, to a same metal atom, but two donor atom is different, so it is known as unsymmetrical bidental ligand. Next we discuss another one is polydental ligand. The ligands which possess more than two donor atoms, which donate more than two lone pair of electrons simultaneously to central metal ion forming a complex known as polydental ligand. If three donor atoms there, then known as a tridentate. Four donor atoms there, known as a tetradentate. Similarly for 5 and 6, pentadentate and hexadentate ligand. Suitable example is EDTA. Suitable example EDTA. That is ethylene diamine, tetraacetate ion. Mark that. It is an example of a hexadentate ligand. Mark that. Ethylene diamine, tetraacetate. Here two nitrogen atom is there and 4 oxygen atom is there. Mark that. Two nitrogen atom and 4 oxygen atom. It is a hexadentate ligand. Contain 6 donor atom. Donate 6 pair of electron with the central metal ion. Then it is known as polydentate ligand. Monodentate ligand, bidentate ligand, polydentate ligand. Next we discuss about ambidentate ligand. What do we mean by ambidentate ligand? A bidentate ligand having two donor sites, but at a time only one donor atom donate a pair of electron with the central metal ion forming a complex. Then it is known as ambidentate ligand. I repeat again. A bidentate ligand having two donor sites is there, two donor atom is there, but at a time among them only one of them donate a pair of electron with the central metal ion forming a complex known as ambidentate ligand. For example, NO2 minus, Cn minus, SCn minus, etc. It is an example of ambidentate ligand. Mark that. For example, NO2. When nitrogen atom donate a pair of electron, here nitrogen atom, oxygen atom, both have the capacity to donate a pair of electron. But when nitrogen donate, then it is known as, its name nitrito-N. On the other hand, when oxygen donate, then it is known as nitrito-O. Similarly, cyanide. Mark that here carbon has a capacity, nitrogen also has a capacity. But at a time only one of them donate. It is known as cyanido, NC, isocyanidol. These are known as. Similarly, when S donate thiocyanate, when N donate isothiocyanate. These are some examples of ambident ligand. Next we discuss chelating ligand. What do you mean by chelating ligand? A bidentate or a polydentate ligand, when donate more than donor atom to a single central metal atom, forming a ring-like structure, a cluster-like structure, then that ligand used is known as chelating ligand, and the ring-like structure form known as chelate. For example, mark that ethylene diamine. When two ethylene diamine diamine, example of a chelating ligand. Mark that it is a bidentate ligand, ethylene diamine. When two ethylene diamine donate to a copper ion, Cu2 plus ion, forming a cluster, ring-like structure, then this complex part, this cluster part or a ring-like structure is known as chelate. The ligand used for the formation of chelate is known as chelating ligand, and the process of formation of that chelate is known as chelation. Next, we discuss last one, that is known as bridging ligand. Last type of ligand, that is known as bridging ligand. Bridging ligand. What do we know by bridging ligand? A ligand which coordinate simultaneously with itself with the two other similar or different metal atoms. I repeat again, the ligand which simultaneously coordinate with two similar or different metal atoms along with itself, forming a connector or forming a bridge, then that type of ligand is known as bridging ligand. That ligand make a bridge connector between the two different or similar metal atoms. For example, OH minus, Cl minus, Br minus, NH2 minus, NH2 minus, etc. These are some ligands behave as a bridge between the two metal atoms. These are some type of ligands depending upon the number of donor site. Most important thing that depending upon the number of ligating site, depending upon the number of coordinating site present in a ligand, it is known as its denticity. If one donor atom donate a lone pair forming a coordinate bond, known as its denticity is 1. Bidentate ligand means its denticity is 2. Next, mark that we represent one structure for a complex. This one example of a complex, mark that. Here, this part is known as non-ionizable part. while this part is known as ionizable part. Mark that. In case of non-ionizable part, a square bracket is there. This square bracket is known as coordination sphere. Coordination sphere or coordination entity. I repeat again. In a complex part, a square bracket is there. This square bracket is known as coordination sphere or coordination entity. Just after the square bracket, one metal atom, that is cobalt, is there. It is known as central metal atom. Central metal atom. Just after the central metal atom, what is present? It may be ion or a neutral molecule. This is known as a ligand. Just after the ligand, a number is there. This number represents the secondary valency or coordination number. Coordination number. The outer side of the complex part is known as ionizable part, or otherwise it is also known as a counter ion. And this number represents oxidation number. So let us discuss one by one. Some new terms are there. Point one is coordination sphere or coordination entity. What do you mean by coordination sphere or coordination entity? Mark that. In a complex part, a square bracket is there. Inside the square bracket, whatever may be there, they behave as a single unit. This is known as coordination sphere or coordination entity, which is a non-ionizable part. Next one is ligand. What is ligand? Already over. It is an electron-rich species which donate at least one pair of electron to the central metal atom. Central metal atom, it may be atom or ion which is electron deficient species, always accommodate, always accept minimum of one lone pair of electron by the help of coordinated bond through the ligands. Next, we discuss what is coordination number. Coordination sphere over, central metal atom over, non-ionizable part over, ligand is over. Next is coordination number. What do you mean by coordination number? It denotes the number of coordinated bond present in the complex, which is a form made by the ligands with the central metal atom. I repeat again. The number of dative bond formed, the number of coordinated bond formed by the ligands with the central metal atom is known as its coordination number. If it is a monodendron ligand, then the coordination number is equivalent to the number of a monodendron ligand. If a bidendron ligand is there, coordination number is equal to 2 into bidendron ligand, number of bidendron ligand. For example, mark that. Let us discuss in some complex CONH3 6Cl3. Here it is the central metal atom, it is the ligand, monodendron ligand, 6 monodendron ligand is there. So C dot N, coordination number of cobalt is 6. Another example, tetramine, copper 2 sulfate. Mark that. Here also monodendron ligand, 4 monodendron ligand is there. So C dot N of copper is equal to 4. Another example. Mark that. Here it is the central metal atom, it is a ligand, it is a bidendron ligand. So C dot N of chromium is equal to 2 into number of binding ligand. It is a monodentate ligand, 2 are there. So 2 into 1, that means 4 plus 2. Coordination number is 6. I repeat again. So coordination number is equal to number of dative bond formed by the ligands with the central metal ion. Next we discuss another one is there, that is oxidation number. Next part is oxidation number. What is the oxidation number? Coordination number, always we have to calculate the coordination number of central metal atom. Here also oxidation number, we have to calculate oxidation number of central metal atom. What is the oxidation number? It is the residual charge of the central metal atom, or possess or appears to have the residual charge possess or appears to have when combines with other atom in the formation of a complex is known as oxidation number. The question is how to calculate the oxidation number. 2 to 3 steps we have to follow for calculation of oxidation number. Mark that. For example, in a complex, we have to calculate the oxidation number of central metal atom. 2 to 3 steps are there. Point 1. While calculating oxidation number of central metal atom, it is not known. Let it is X. Then point 2. Sum of the oxidation number of total complex if it is neutral is equal to 0. If it is ion, then sum of the oxidation number is equal to its charge. Next point, oxidation number of ligands, if neutral are there, then it is 0. If charge species is there, then its oxidation number is equivalent to its charge. Mark that. For example, we have to calculate the oxidation number of copper, let it is X. It is neutral, so 4 into 0 plus sulfate ion, it is SO4 2 minus, so it is minus 2, 1 into minus 2. R it is neutral, sum of 0, so X is equal to plus 2. This oxidation number is represented in Roman numerical within a parenthesis. I give another example. K4 FeCN6. Mark that. Here central metal atom is iron. We have to calculate the oxidation number of iron, let it is X. Potassium, valency is 1 plus, so 4 into plus 1 plus X plus 6 into cyanide ion minus 1, neutral it is 0, so it is equal to 4 minus, that is X, minus 2 is equal to 0, implies X is equal to plus 2. The residual charge is known as its oxidation number. It is represented in Roman numerical within a bracket. So next part is we have to discuss now the IPSC system of, that means the systematic way of naming the complex compound. Mark that. CONS36 Cl3. It is one complex. K4 FeCN6. It is another complex. So from this we have another one also there, NiCO4. Mark that. So from these 3 examples, it is clear that the complex compound or coordination compound are of 3 types. One is cationic complex, one is anionic complex, one is neutral complex. Mark that. This one is a non-ionic part, it is ionic part. So this one is a cationic part, so it is known as a cationic complex. Cationic complex. Mark that. Here is the ionizable part, it is the non-ionizable part, the complex part is the anion, so it is known as anionic complex. Mark that this complex never break down, it is a non-ionizable part, no cation anion is there, so it is known as a non-ionizable complex. That means complex are of three types. One is cationic complex, one is anionic complex, one is non-ionic complex. So whatever may be the nature of the complex, there are some rules are there. First rule, always name of the cation first followed by the name of anion, whether the complex is cationic, anionic, non-ionic. I repeat again. The name of complex part, while giving the name of a complex, first give the name of a cation, then anion, irrespective of the nature of the complex, whether cationic, anionic or non-ionic. So mark that, what is the cationic part is there. Here cationic part is a complex part. So how we give the name of a complex part? While giving the name of a complex part, in a complex part, two type of species is there. One is known as central metal atom, rest are ligands. Ligands are of three types: cationic ligand, anionic ligand, neutral ligand. So whatever may be the name of the, whatever may be the type of ligand, nature of the ligand, first name of ligand is given, followed by name of central metal atom. If more than one type of ligands are there, no problem. Name of the ligands are given in the alphabetical order. I repeat again, three types of ligand. If there is anionic ligand, come to the point one. If anionic ligand is there, then its name ends with O. Whatever may be its name for anionic ligand ends with O. For example, Cl minus, mark that. Normally it is chloride. So remove last letter, add O, chlorido. SO4 2 minus, sulfate. Remove last one, add O. CO3 2 minus, its name carbonate. Remove last, add O. In case of anion ligand, chlorido, bromido, hydroxido, sulfato, carbonato, acetato, etc. In case of anionic ligand. For neutral ligand, no special name is there. For example, for neutral ligand, no such type of naming is there. Mark that. NH3 known as amine. H2O known as aqua, NO nitrosyl, CO carbonyl, PY pyridine. These are some examples of neutral ligand. Next is cationic ligand. If cationic ligand then ends with IUM. Mark that. NO plus nitrosonium ion, NO2 plus nitronium ion, etc. So whatever may be the nature, type of ligands are named alphabetically first. If ligands are one type of ligands repeated two or more times, then you use prefix di, tri, tetra, etc. The most important thing, di, d, tri, d, these are not included for checking the alphabetical order. And another one important thing is that if a name of ligand is di, tri is there, then if they repeat two times, three times, instead of di, tri, we use bis, tris, tetrakis, etc. For example, En, its name is ethylene diamine. Mark that. Already it is a di is there. So if En2, two molecule is there, instead of diethylene diamine, we use bis ethylene diamine, and it is represented in form of a parenthesis without give any space between them. So after naming the ligands in alphabetical order, next come to the name of the central metal atom. Mark that. Again, two types is there for giving the name of the central metal atom. So central metal atom may be present in cationic part or in anionic part in a complex. If cationic part is there, no separate roles is there, just write the name of the central metal atom followed by in a parenthesis in a Roman letter we write its oxidation number. I repeat again. If the central metal atom in the cationic part, then we write only the names of the central metal atom followed by in parenthesis inside which we write its oxidation number. On the other hand, if the anionic part is there, central metal atom present in anionic part, then we have to write its Latin name of the central metal atom followed by parenthesis its oxidation number. So let us discuss one by one. Here, our first point is followed by cationic part, then anionic part. Cationic part is a complex, so first ligand, only one type of ligand, repeat 6 times. So the last one, the most important thing is that name of a complex is a single word. If it is a neutral, then non-ionic, then it is a single word. If ionic part is there, then complex part is 1, then the space between the counter ion. And always most important thing is that name starting is a small letter. So mark that it is hexamine. Hexa A and amine A both are there. Hexamine, name of ligand part is over. Next, central metal atom. Central metal atom is a cationic part, so cobalt. Then followed by parenthesis. Then give space to write chloride. We have to find out its oxidation number. Mark that. Its oxidation not known. Let it is X. 6 into neutral molecule 0 plus 3 into it is minus 1 is equal to 0. That means X is equal to plus 3. That is we write hexamine cobalt 3 chloride. Mark that. Another example. CuNH3 whole 4 SO4. It is the cationic part. So first we write the name of the ligand. It is amine. Important thing, remember that while writing amine, double M is there. And 4, so tetraamine. Tetraamine. Ligand part over. Next, central metal atom, copper. Followed by parenthesis, gap, sulfate. So its oxidation not known, let it is X plus 4 into 0 plus minus 2 is equal to 0, X is equal to plus 2, it is Roman letter II. Let us one example of anionic complex. K4 Fe CN6. Mark that. It is the anionic part and anionic complex. So whatever may be the nature of the complex, first cation followed by anion. So cation part is small letter potassium space. In case of complex part, first we write the name of ligand. It is cyanido. 6 is there. Hexacyanido. And next, name of the metal atom. As the metal atom in anionic part, we have to write its Latin name. That is ferrate. Followed by parenthesis, we have to write the oxidation number. That it is it is 4 plus 1 not known x, 6 into minus 1 is equal to 0. That means on solving x is equal to plus 2. Another example, K3 FeCN6. Mark that. Similarly, we write potassium space hexacyanido ferrate followed by oxidation number. Mark that. It is plus 3 plus x plus 6 into minus 1 is equal to 0. On solving x is equal to plus 3. These are some examples of anionic complex. So cationic complex over, anionic complex over, then we switch over to non-ionic complex. Some examples of non-ionic complex. Tetracarbonyl nickel. Mark that. It is a non-ionic complex. So it is represented in a single word. Whatever may be, first name of ligands, then metal atom. So ligand is known as neutral ligand, carbonyl 4 times. So tetracarbonyl followed by name of metal atom followed by parenthesis. It is X. It is neutral plus 4 0 on solving x is equal to 0. So its name is tetracarbonyl nickel 0. Mark that. Another example, FeCO5. Similarly, its name is pentacarbonyl iron. Mark that. It is X plus 5 into neutral 0 is equal to 0 on solving x is equal to 0. So its name is pentacarbonyl iron 0. So these are some examples of cationic ligand, anionic ligand, and last one is non-ionic ligand.